Greeting everyone. My name is Maxime Toussaint. I will be the representative of the Beavers teams, and let's have some fun together. So first, let's give some context on our contribution. It was our first time using Surf, Sil, Stir, and for my case in particular, TensorBoard. So it was kind of a fun way to learn things. And we decided to start small by just saying, hey, we want to play with LBFGS because recently there have been nice development in this algorithm for doing stochastic approach for optimization. But the motivation for this was first we know that higher order method of our algorithm are known to shine when we are near the solution, and we had observed that the Petric challenge was providing free of charge already pretty good image for the data fidelity term, so made sense to start from there. And spoiler, we didn't get to do the LBFGS, but we still had some fun. So before we start to run by doing the LBFGS, we wanted to start to walk. It is not the easiest algorithm to implement in a way that is efficient for Python. So we did us a little checklist of things to do. Well, first, need to know how to use Surf. After that, we wanted to be able to see if we were able to provide a pretty good first initialization image for the regularized problem. After that, we wanted to have an efficient implementation for the line search, since this is required for the algorithm. And last but not least, do the magic. For our approach to test the first 3 points was to base ourselves on the provided BSREM algorithm in the Surf, and also using the Mages team's algo 1, which was the third best at the last challenge. So our first contribution, a smoother initialization. Our motivation, we know that in terms of graphic path reconstruction, CT also, when we do reconstruction, we first recover low frequency structure, and then we slowly go to the higher frequency structure. And we also know that it is hard to remove high frequency structure from the image. So our idea was to provide, and we also observed that the install image provided by challenge was kind of noisy and with pretty much big artifact. And we also estimated that any structure that had the frequency that was equivalent near enough of the theoretical spatial resolution of a given scanner made no sense for a starting point. So our proposal was to simply convolute the initial image with a Gaussian filter following a scaling of the theoretical spatial resolution of the scanner. Let's see what it provides us. So we applied this algorithm to the BSER1 provided at the Surf. So in short, whenever I do a comparison, the lighter color will represent the vanilla algorithm, and the darker color will represent our modification of said algorithm. So here we have the RMSE of the whole object. In green and in blue, I show you cases where doing the convolution gave us a great boost in speed to obtain a good RMSE for the algorithm. And in red, you can see cases where even if we started greatly with our convolution, well, at the end, after 90 iteration, it didn't change much in terms of performance. Now we wanted to try this with an algorithm that was known to be highly performant. We applied that on the algorithm 1 of Mages. A brief description of the algorithm is that it is a stochastic variance radius gradient that uses a preconditioner. The number of subset was a number of u that is near enough a divisor. It was near the divisor. Yeah. The number nearest of 25 that was a divisor of the number of u's, and the preconditioner also only use the data fidelity term and also the prior. The only modification we applied was in 3 steps. First, we applied the filter that we talked previously. After that, we changed when the preconditioner was updated, moving them from the end of the epoch to the middle of them. And we modified the rule of the step size, being they are updated faster and they are decreased a little slower. Those 2 last ideas was following the observation that the Petrix 2 challenge seems to be easier, less requiring in terms of iteration to converge, and thus changing this approaches. So what you see right now is what happens when we apply this modification to the algorithm compared to what was the vanilla implementation. And again, in case of blue, you can see that having a smoother initialization image gives a great boost at the start. In the green case, you can see a situation where the modification of the preconditioner and the step size give you a great boost on when you start to really increases in terms of the matrix of interest. And the brown vs golden case is a great case of where the modification provided a significant boost in performance. So our second contribution following from that was to have a good enough step size. The goal was to be able to, if required, depending if we're a slow progress, a plateau, or just at the start, to be able to say, here's a good step size to use from that. And before doing it for every kind of solution, we just wanted to be, hey, let's have a good initialization for the step size. The approach we used was simply, we wanted the step sizes that have satisfied the wolf condition, which are described as follow on the lower part. In short, we want it to ensure that you progress enough in terms of the objective function and that you decrease enough in terms of curvature. We simply use the algorithm provided by SciPy to do the search of the good enough step size. And the parameter we used was vanilla for the term of curvature, but we increased the criterion for the objective function. Just to give you an intuition of what happens when we change that criterion, in short, if you use the basic approaches, you have like, it forces a great update on for the objective function with a step, and by increasing the value, you are more permissive in what it can go from there. In terms of computational detail, we wanted this to be not too costly because it is a competition in terms of computation time. So we did an evaluation of the const function that used only half of the subsets to evaluate if the step size was good. And just a mention of interest is that when we did that, it was a start. So we used the first subset to evaluate the direction of interest, but to evaluate if it was a good for all subset, we use all for the subset, excluding the one we use for the direction, thus hoping that it will be more stable for every subset of interest. Also, by using a tricks with the forward projection, we know that we don't need to evaluate every time that we check for a step size if it is good enough by doing the forward projection of the image and the direction, thus saving some time in computation time. And this problem with that is that we ignore what happens when we have negative value for this kind of line search. But let's hope that it doesn't do too much problem. So now we applied this to the provided BSAR algorithm, and we have the following result. In short, the red cases show you a situation where the proposed modification was a problem. It provided us a too small step size and thus was not converging quickly compared to the basic value that was already there. And the black cases show you two cases of interest of the green and the blue, where after some time we observed that our initial step size provided a good, probably good idea of how to progress from there. So, closing for them, learning surf on the go was not optimal. It was kind of a hard but challenging process. TensorBoard is nice when you first want to check a couple of them, but quickly it becomes clunky, or maybe it is just my regex skills that are limited in that situation. And I tip my hat to the Macis team that had proposed to do a sandbox before doing testing, because it was really complex to try to test many IDE when it took so much time to do any testing. Thank you very much.